And along with that one, some important very concepts of the collisions. So now this is the one thing we are energy and the power we'll be discussing, and in this one we'll be discussing the work done by the constant force and the variable force here, law of conservation of energy, elastic collisions, oblique and coefficient of restitutions, and the different cases of the rebounding of the ball after collision from the ground. So coming to the first one, work done. So work done by the constant force. What is your work done is going to be the so work done can be written as and work is nothing but an it's a transfer of energy. So by doing certain work, you are transferring the energy from one form to the another form. So or else you can call it as an so when a force when a force produces some displacement, so you can call it as an work done. Fine. So that means W or the work done is equal to force into displacement, or W is equal to F bar dot S bar, or it is Fs cos theta. So the force which is responsible for the moment, just if we go for the basic thing, the force which is responsible for the displacement of any particular object. If a force is applied in this direction making an angle theta, then F cos theta is the one which is responsible for the block to move from certain point to the certain point here. Suppose this is the point A to the point B here. Okay, so now we are causing a displacement of something, yes. So this can be written as and the same thing, F bar dot S bar is equal to Fs cos theta. Here the work done is nothing but an amount of energy that is transferred. Suppose it might have certain velocity u is equal to 0 starting from the rest. You are giving by doing certain work transfer of energy in the form of the kinetic energy. So your work done can be positive and as well as the negative. So that is in the sense if theta is equal to or less than 90 degrees, then work done or the W is equal to Fes, which is the positive work, it is called as N. That is the positive work. And if theta is going to be greater than 90 degrees, work done will be the minus Fs, that is an negative work. So now in this case, or else if theta is equal to 90 degrees, that means force and the displacement are perpendicular to each other, then the work done will be 0 in this cases. So now when we see the variable work done conditions here, that means see, this is the case where we have seen the work done by a force is going to be the constant thing. So now if we go for the work done by a variable force, so in this case that means force is changing with respect to something or at any instant if the force is going to be changing. For example, there is a system sort of a thing like this. There is a block whose mass is going to be the M, and we are applying certain force on this one. And this block has been making certain displacement over here of the S, something is here. So now, if the function or if the force is a function of the X, that means it is changing with respect to the X, then that every instant there is a change in this particular thing, that this position be x1 and this position is going to be the x2, then work done in moving it smallest displacement dw can be written as an f of x or f bar dot, that is your dx bar, or the total work done can be obtained as an w is equal to integral of dw, in the sense integral of F bar dot dx, where x values are changing from the x1 to x2. So like this, you can go for that variable thing. If at all, the force is a function of the time, and this is going to be your dx bar. So if it is a two-dimensional structure, you can write it as an dx bar, or if it is a two-dimensional or three-dimensional, sorry, yeah, straight line, you can directly write it as a dx or dy or anything, depend upon the function of the force. If it is a three-dimensional thing, then the same thing can be written as an work done W is equal to integral of some function or f bar. It's a vector like this into, that is dr bar. Here dr bar can be written as an, it will be the dxi plus dyj plus dzk. So depend upon the type of the force that is being used. In the sense, suppose if f bar is equal to some xi plus yj plus zk thing, then you need to take this a position vector with respect to the origin and substitute the limits some x1 comma, this is y1 comma, and this is your z1 to the values x2 comma y2 comma z2. So please be careful of this one. So if it is a two-dimensional or three-dimensional thing, you need to go for the dr bar, where dr bar will be equal to the dxi plus dyj plus dzk. So this is the case. Suppose if I want to go for such an example in this case. So in the structure, suppose if a force is a variable, as we have seen, F is equal to some sort of an 2x square plus, that is 3x plus 1 is a force. You want to displace it from certain position to, or I want to move it from certain position. X1 is equal to 1 meter to the x2 is equal to 2 meters with respect to a coordinate system. We are just moving it with respect to along the x-axis here. There is a block over here, and that the mass is going to be some 10 kgs. You are moving in this case. A force is applied in this case. At the initially x is equal to 1 is there. Oh, this is the condition. This is your x-axis, and this is your y-axis. So how do you calculate the work done for this one? So W is equal to integral of, this is f bar dot some dx bar, substitute this, replace the x, which is 2x square plus 3x plus 1 into dx, where your x values are changing from the 1 to x2 is equal to 2. So at this particular instance, it has been changing. You need to just go for the integration. It will be the 2 into, that will be the x cube by 3, limits ranging from 1 to 2, plus 3 of, this is x square by 2, limits ranging from 1 to 2, plus x 1 to 2. On substituting the values, whatever you will be getting, that is 3 by 2 into 2 square minus 1 square plus 3 by 2 into, it will be the 2 square, sorry, 2 cube minus 1 cube, 2 square minus 1 square, and the last section is 2 minus 1. On solving this one, you should be getting your work done in this case. So now the area under the graph of the work done, the area under the graph of force into displacement, force versus displacement, should give you the work done. Suppose your force is along the y-axis and displacement x is along the x-axis here. So force, let the force is some function of x like this, some sort of a parabolic shape in this case. So you can have the work done in this case is going to be the area under this particular thing will give you the, this is x1 and x2. So this entire area will provide you the, this is your work done. Fine. So this is another important case, please. Or else you can go for the vectorial conditions also. If the force is given in terms of the vectors, directly you can find the work done as a scalar product of the things, please. So now coming to the law, as we have told that the work done, whatever the work done is there, that is been converting in the form of an, or you are transferring the energy from one form to the another formation. So this law of conservation of energy statement, according to this one, so the energy neither be created nor can be destroyed in this case. That statement you know. So from this one, you can say that whatever the energy is going to be there, energy will be energy remains. It's going to be the constant, or it's going to be changing its state from one format to the only the another format. Okay. So conserved means whatever the energy is there, total energy, and that total energy is being taken into the another format. Or else, suppose whatever the work done, suppose if you are doing, the work done is equal to our work energy theorem. If you consider, the work done is being converting in the form of n from half u square to the half mv square. So it is staying in the form of the kinetic energy here only. Suppose if you go for the potential energy, it is minus of delta U. In some situations, it might be this kinetic energy might be mechanical energy will be converted into the two formats. That is, in the sense, potential energy will be converted into the kinetic energy, or kinetic energy will be converted into the potential energy situations, please. So these are all for the conservative forces nature. So for the conservative forces, for the conservative forces, your force or the work done will be equal to zero. That does not depend upon the path. Initial and final points only. It's going to depend upon. Then your change in the work done or delta W will be integral of F bar dot. It's going to be the dx bar, which is equal to the minus delta U. And you can say that for the conservative nature, F is equal to minus of du by dx, or you can call it as an du by dr or anything, or in the general cases, if you want to write, it is I cap minus, or this is dou u by dou x along the I direction, or dou u by dou y along the j cap, and minus dou u by dou z along the k cap directions, please. So these are your situations, please, or the same thing can be written as an. So F can be written as an, or F bar for the mathematical application, F bar can be written as an minus of delta U, which is called as a negative of gradient of your potential energy. So your gradient means that is delta is called as an is equal to the dou by dou x of I cap plus dou by dou y of j cap plus dou by dou z of k cap. So this is also you can delta variant also you can use for solving the sums. So in the different cases or in the different situations, this will be useful for you. Please. So as we have given you the energy conservation, it can be transferred from the one form to the another form. So the both the mechanical energies it can be transferred. If there is a spring is there, it will also transfer to the energy stored in the spring also it will be conditions. So like that it will be transferred depend upon the situation. It can also be transferred in the form of the heat also. So based upon the question you please judge whether in which format it's going to be converting, please. Okay, so now coming to the elastic collisions and all these things. So coming to the collisions, what do you mean by collisions, sir? So what happens in the state of the collisions? So the momentum will be transferred by the internal forces of the system. You can say that one. So in this cases, there will be that majorly there are the two types of the collisions that everybody knows: the elastic collision and inelastic collisions or perfectly elastic collisions. So it is a process where it is a process of transfer of internal energy or process of movement by the sorry internal transfer of excuse me this one uh, momentum by the internal forces, transfer of momentum by internal forces. So in the sense, suppose there is a two balls of masses, one is called as an M1, another one is called as an M2, moving with the same direction, that is, this will be the U1 and this will be the U2. Obviously, it is certain that U1 has to be greater than the U2 for the collisions to be taking place. So at the collision instant, what will happen? So both of them, due to forces or internal forces, will be in the opposite sense like this. So one will be the mass m1, another one is going to be the mass of m2. So at this state, and at this particular instant, what will happen during the collision? I'm talking during the collision. During the collision, very important points, man. Collision, your kinetic energy will come down to the minimum, and m1 and m2 will have same velocity, and potential energy, that is PE, will be extended to the maximum. So this is because during the collision there will be deformation will be occurring. So since the shape and size of the both the bodies which are colliding is been changing, that means the body has been deforming. Since the bodies are deforming, the potential energy will be more in that one, and at this instant both of them will be traveling with the same kinetic energy. And when the body is going to be regained its original shape and size, then whatever the energy that is converted in the form of the potential energy will be again transferred to both the bodies in the different velocities. This might be the V1 and this might be the V2. So if the transfer of the potential energy after the deformation is completely transferring, then that type of the collision is going to be will be equal. You can call it as an elastic collision, where if the transfer of the potential energy is partially happening, then you can call it as an partially inelastic collision. Or if the transfer of the potential energy is going to be very minimum, that means the bodies continue to be in the form of in the deformation state. You can call it as an perfectly inelastic collision, where there will be the loss of energy and the kinetic energy will be lost. Fine, sir. So this is the main basic thing. And in the perfectly, as we have told, that perfectly elastic collision, your transfer of the potential energy at the deformation stage will be completely taken out. So now in this situation, for the perfectly elastic head-on collision, that means this is the same thing. Both the bodies are traveling in the same straight line, and one body is colliding with another body here. So during the collisions, the deformation is been happening. Since the deformation is been occurring, and they are transferring of velocities, and after that it's been happening. So in the elastic collision, the first one, in elastic collision, in elastic collision, what will happen? Your law of conservation of the momentum and law of conservation of the energy or kinetic energy, both are going to be the conserved. So both are going to be the conserved in the sense the in this case, yeah, very good. So because they have been conserved, that means you can say that m1 that means m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. This is the condition for the law of conservation of the momentum. And coming to the conservation of the energy, that can be written as an half m1 u1 square plus half m2 u2 square is equal to, that will be the half m1 v1 square. This is half m2 v2 square. For example, these are the equations that we are writing. This is the before collision equations. These are after collision equations. Suppose in the question or in the examination, if he asks what is the common velocity during the collision, then you need to be very careful. Or if he asks you the potential energy is going to be how much during the collision. Now I'm going further. During collision. So what is happening during the collision? As I have told you, the initial momentum, whatever is there, m1 u1 plus m2 u2 is equal to your m1 plus m2 into the velocity will be the common at the time of the collision. So since they are retaining the common velocity and that is going to be the minimum, your kinetic energy will be minimum at the time of the collision. So from this one, the velocity, both the bodies will have the same velocity, that is m1 u1 plus m2 u2 by m1 plus m2 will give you the velocity of both the bodies during the collision. Now, if we ask you to find out the potential energy during the collision, so how can you get the potential energy in this case? So as it is under the case of the conservation of energy, your potential energy will be the nothing but a difference between the potential, whatever the final potential energy is there, that is kinetic energy, that is half m1 plus m2. Both of them will be moving with the same velocity during the collision, and this is half m1 u1 square plus half m2 u2 square. This is during the collision. If the question he asks you in this case particularly. So why we cannot use MGH in this particular situation? Because one thing, the bodies M1 and M2 are not changing their position, in the sense they are not changing their heights or anything. For your understanding, I am taking the word called as an heights. So that means their position is not changing. Then what is changing, sir? They are changing their shape. So that means the spherical shape, they are going to be undergoing the deformation. That means during the collision, what will happen? Suppose M1 might be retaining its original shape, but M2 might be changing its shape to the another one like this. It might undergo its shape change, deformation might be taking place. So this cannot be expressed in terms of the MGH, right? So this is how you can go for an during the collision, the potential energy conditions. Now, after collision, what will happen? After collision, you can solve these two equations, that is the law of conservation of the momentum and law of conservation of the energy, to get the values of the V1 and V2. You can get it comfortably. Two values are unknowns, V1 and V2 are the two unknown values. You have got the two equations, two unknowns, two equations are sufficient to solve the sums. So coming to the after collision conditions. After collision, then the velocity will be equal to the, or the velocity of the first body will be equal to the, it can be written as an m2 minus m1 by m1 plus m2 of u1 plus 2m2 u2 by, this is m1 plus m2. So this is the velocity of the first ball after collision, and v2, that is the velocity of the second ball after collision, can be written as n, that is m1 u1 by m1 plus m2 plus, this will be the m1 minus m2 by m1 plus m2 of, this is u2. So using these two relations, you can determine the velocities after the collisions in either case, that is V1 and V2 values. Depend upon the situation that is given in your sum or the application. That means if he mentions that velocity of the second ball or the second ball is in the rest position, that means U2 will become 0. Or if both the balls are traveling in opposite direction, then instead of the minus plus sign here, you will be getting the negative sign. For all the cases, definitely U1 has to be the greater than the U2. In this cases, unless this one happens, you cannot have the collisions and you cannot have the perfectly elastic head-on collisions, please. So now this is the one such thing. There are the different cases in this elastic collisions. So what are these different cases in this one? As we have written the formulas, V1 is equal to, that is m1 minus m2 by m1 plus m2 into u1 plus 2 m2 u2 by m1 plus m2. And your second velocity v2 can be written as an 2 m1 u1 by m1 plus m2 into of, this is m2 minus m1 by m1 plus m2 into u2. So in this case, suppose if case 1, if I want to take that, in the sense u2 is equal to 0, that means second body is in the rest case. The same values can be written as an, that is v1 is equal to u2 is equal to 0. u1 is there. It will become as an m1 minus m2 by m1 plus m2 of u1, and your v2 is going to be converted as an 2m1 u1 by m1 plus m2. Or in this case, case 2, same situation, if I take u2 is equal to 0 and your m1 is equal to m2, or u2 is not equal to 0 also, if you want to go, so you can take that particular thing also. That means if I remove this particular thing, both the m1 and m2 are same, then the velocities will be exchanged. If m1 is equal to m2, your first term in the v1 will be cancelled. The only term that will be left over is going to be the u2, and v2 is going to become as an u1. There will be the exchange in their velocities. There will be the exchange in the velocities. And the third case, if I take the same thing as an upper one, if u2 is equal to 0 and m1 is equal to m2, then in that situation, then v1 will become 0 and v2 is equal to u1. So if I want to go for the next case of this one, that means fourth case, where if u2 is equal to 0 and m1 is going to be the very greater than the m2. And that means heavy body is coming down and hitting a light body. So in this situation, what will happen? Then v1 is equal to, obviously your second term will be 0. You are left with m1 minus m2 by m1 plus m2. Since here m1 is very much greater than the m2, that means you can neglect the m2. So when we neglect the m2, it comes down to be the v1 is equal to u1 and v2 is equal to. So in this situation, in the second case, this will be obviously second term of the v2 will be 0. First term will be there. In this m2 you are neglecting, remaining is going to be the 2u1. So like this, you can adjust to the depend upon the situation and choose the values of the final velocities v1 and v2. Don't forget, this is purely the head-on elastic, perfectly head-on. That means the collision is been taking place in a straight line. So please be careful, or please remember that particular point. And in this head-on collision, for solving the sums, you can also use another relation, which is very important case. That is the relative velocity after collision v2 minus v1 is equal to u1 minus u2. That means, so what is this one is a relative velocity after collision, after collision is equal to, this can be written as a relative velocity before collision, before collision. Fine. So this is another very important relationship that can be useful for us. Okay. So in the head-on collision also, in the elastic head-on collision itself also, you will have an oblique collision sort of a things, please. That means the collision might be taking place with certain angles uh, in the like this, or this head-on collision. You can also use it for an last or particle collisions or the nuclear collisions in the case. For example, there is a, if you want to take it as a neutron, there is an, so a neutron is there, so moving with certain velocity is some v, and it is colliding with an a stationary nucleus. So this is, that means u2 is equal to 0 in this one. So this is u1 is equal to v. And after collision, what can happen? This one, let the masses of this one is, this might be traveling with a velocity v1, and the nucleus might be traveling with the velocity of the v2. So now how to find out this one? That is v1 is equal to, we know the formula m1 minus m2 by m1 plus m2 in this case. And mass of the each nucleon, if you consider it as an m, then, so how do you write this particular thing, please? So mass of the neutron m minus m into a by m plus m into a, moving with a velocity v, obviously your second term will be 0. In that sense, the un can be written as, and this is 1 minus a by 1 plus a, where a is a mass number of this one. What is a? This is the mass number. Okay, so into v. And similarly, you can also find the velocity of the second one is going to be how much? So as u2 is equal to 0 in this one, you can also find this one 2 m into, this can be written as an v by, this is going to be the m plus a into m, remove the m here, which will be the 2v by 1 plus a, he can unlike this. So the question can be extended to, you can find the ratio of the kinetic energies of both of them after collision like that. You can use whatever may be the situation there. Okay, so please be careful of that one. So next we'll be going for an oblique collision conditions, please. So what do you mean by this oblique collisions? Oblique collisions means if two particles are, or two bodies are colliding with making certain angle towards each other. So first one, I'll go for a general or the basic oblique collision. Oblique collision. So in this one, for example, if you go for an, so a ball is there, a ball is been taken and it has been hit on the surface, and the surface is a fixed, or you can consider it as a ground. So obviously this will be your normal. If I take this to be the normal one, or the perpendicular drawn to the surface of this one, normal or the y-axis, or you can, the ball is being taken like this and it is been passing and it has been colliding at this particular point. So this point is, this line you can also call as an a line of impact. This is also called as a line of impact if you are hitting with an angle called as in some theta 1. So what will happen in this case? It is coming down in this direction with the velocity of the u, means in this one it will be u cos theta 1, and along this one horizontal direction you will have the u sine of theta 1, that will be approaching towards the surface, and after colliding with the surface, this is your normal n. After colliding with the surface, suppose if the ball is been moving with a velocity of some v and making an angle some theta 2, then in this direction you will have the v sine of theta 2, and exactly in the opposite direction you can have the v cos of theta 2 in the upward direction. So if the, I'm strictly considering in this case surface to be the smooth surface, please. Fine. So now in this case, you can, different situations. So the, this is the ball is been colliding at this particular instant, and this will be your line of collision, and the velocities in this case, that is this axis, which is called as an x-axis. We can also call it as an t-axis. I'm calling it as an, that is tangential axis. So along the t-axis, what will happen? Along the t-axis, so your momentum or the velocities before is equal to velocity after the collision. Or the momentums will also be the same in that sense. U sine of theta 1 is equal to V sine of theta 2. So this you can use it please here. If the angles are same, that's a secondary issue. Or else in another cases, these two are in the opposite direction, that is along this axis, you can call it as an n-axis or normal axis. So in along the normal axis, what will happen, sir? So you will be applying, or the impulse will be transferred, or the internal forces will be transferring the momentum. In that case, that means the change in the momentum before collision is equal to change in the momentum after collision. So this is going to be happen along your n-axis, and if you have the coefficient of restitution, that will also be the valid in that along the n-axis conditions. Okay, so this is one of the basic thing regarding the collisions, sir. So if I want to find out the velocities or the final velocities and all these things, so how to take this one? So along this direction before collision means that is going to be the mu. This is cos theta 1 is equal to mv cos theta 2. M cancels this one. Let this be the equation 1 and equation 2. If you square them and add them, first equation plus second equation square, you can get the relationship between the velocities of these two things, that is sine square theta 1 plus that is v is equal to, you will be getting it as an u situations please, or u square is equal to v square, or v is equal to u. So this is the one type, this is an oblique collision on a flat surfaces. So the same oblique collision can also be happening on the two-dimensional thing also. It can also be in the two-dimensional structures. So how can this particular thing happen? For example, here there is a mass called as an some m1, and there is another mass called as an m2. So both of them have been traveling in this direction, suppose, with the velocities of the u1 and another velocity is called as an u2. Let this be the horizontal line or the along the x-axis, and both the bodies are colliding at a particular point here. So this is your tangential axis, which is the t-axis, and this is your line of impact. You can call it as an n-axis, or this is line of impact. So this main thing. Now, after collision, what can happen, sir? So they might be traveling or they might be moving with certain velocities. Suppose this might be the V1 and this might be your V2 values. So let the velocities before collision of this one and the velocity of this one makes an angle sum. This is theta 1 and theta 2 with respect to this one. And here it can be the alpha 1 and alpha 2 after collision. Apply the corresponding principles along the x-axis and y-axis. That is, along the x-axis, it will be the m1 u1 cos theta 1 plus m2 u2 cos theta 2. This is along the tangential axis is equal to, that will be the m1 v1 uh, cos of alpha 1 plus m2 v2 cos of alpha 2. This is our one of the relationships. And along the line of impact, if I want to apply this one, so line of impact in this case, so you'll have only the initial velocities in this direction. That will be the m1 u1 sine theta 1, and in the opposite direction m1 v1 sine alpha 1. You can equate the velocities in this directions also. This will be the m1 u2 sine theta 2, and this will be the m m1 u1 sine theta 1, m2, or this will, sorry, m2 u2. This will be the m2 v2 sine of alpha up to. So you can compare these values also along that particular direction. If it is an elastic collision, obviously it will also be what will be satisfied. Law of conservation of energy will also be satisfied. That can be written as an half m1 u1 square. Total energy I'm writing that is half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. So this is your oblique collisions in the two-dimensional case, please. Now, in the elastic collision coefficient of restitution situations. So what do you mean by coefficient of restitution? Coefficient of restitution. So this is being represented by the small e. So for any particular object, for this one, if a ball or any object is being uh, placed on the surface like this, and it is being collided like this, and the ball is being traveling in the opposite sense in this way, making an angle theta 1 and theta 2. We have written some equations. So it is defined, our actual definition of this one is it is a ratio of the velocity relative velocity after collision by relative velocity before collision. So that means it can be written as an V2 minus V1 by U1 minus U2. So the values of the coefficient of restitution perfectly elastic collision E is equal to 1. For the inelastic collision, or partially you can say E will be ranging between the 0 and the 1. Third one, if it is a perfectly inelastic collision, then E value will be equal to the 0. So what will happen in the case of the inelastic collision? So in the elastic collision, we will be using the both the relations, that is the law of conservation of the momentum, and we'll be using the law of conservation of the energy. But in an inelastic collision, we can use the law of conservation of the momentum, but energy is not conserved in this case, or kinetic energy is not conserved in this situation. So you can go for the use coefficient of restitution along line of impact. So this is the second equation. Instead of the conservation of energy, you can use in an inelastic collision for solving the sums. So in this case, what will happen in an inelastic collisions conditions? A simple thing, if we want to go for a situation where I just want to take an example, that is an a ball is there. For example, if I want to go in this case, a ball is there like this, which is been traveling in this one with certain velocity called as an u, or u1 is equal to u, and let the mass of this one is going to be the m. So this is been colliding with another one, same identical ball. You can call it, you can take for a simple of mass m, which is in the rest position. That means your m1 is equal to m2 is equal to m. Both of them are the identical cases. So this has been colliding. Then what will happen after the collision? Let this axis, or this one is going to be representing its x-axis conditions, and let this be representing its y-axis of the collision, please. And this is your x-axis. Okay, so now if after collision, suppose both the balls are going to be making an angle sum 30 degrees with respect to the x-axis, both the angles are same. 30 degrees with respect to the x-axis. Okay, Ocean, what are the speeds of that basic? That is, let it be the V1, another or V2, another one is called as an V1. So we need to find out these two values, sir. So in this case, if I apply this is going to be your line of impact. This will be your line of impact, and this is your p-axis. So along the tangential axis, velocities are same. Along t-axis, what should happen? Velocities are same. What are the velocities after collision? One will be having this is v2 sine 30 in the upward direction, and the downward direction v1 sine 30. In the sense v2 sine 30 is equal to v1 sine 30. Sine 30 will be cancelled and v1 is equal to v2 is equal to v. Okay, so now based upon this one, apply along n-axis. So when we apply along the n-axis, so that is momentum mu is equal to, that will be the m into v1 cos 30 plus m into v2 cos 30. These are the two values which will be, and v1 is equal to v2, that means mu is equal to, so 2mv1 or v into this is cos 30, which is root 3 by 2, can be removed, u is equal to 2 into v value root 3 by 2 times of the v. So the 2 will be cancelled and u is equal to how much, sir? That is root 3 times of the v. So like this. In this case, if it is an elastic collision, you can use the kinetic energy. If it is not an elastic collision, you can give some value of the coefficient of restitution that can be submitted. Now, in this case, where the rebound of the balls after collision is been taking place with the ground. So that means the balls are been falling or you are been allowing it to fall from certain height. Let the body is being allowed to fall onto the ground from a height called as an h, where its initial velocity u is equal to 0. So since it's been falling onto the ground, it hits the surface and it rebounds to certain height. Let that height be the h1 and down. So this is going to be the h1, and now it's going to be the next one, please. This is going to be your h3, and and this will also be your h3. So like this, it will go on rebounding, and finally, what will happen? It comes to the rest position. If it is containing the rest position, then final velocity will be equal to the zero. So since final velocity is equal to zero and some coefficient of restitution is also there, so the earth, whatever is there, or the ground's velocities are equal to zero. That means let me consider them as an u2 is equal to v2 is equal to zero. These are their velocities at the instant of the collision, at the time of the collision. So the u2 is equal to v2. Now that means the velocity with which it is striking the ground, it is also lifting the ground with the same sort of in initial velocity is equal to zero and your final velocity. So with respect to the ground, the velocities are zero. Let the velocity at this particular point is going to be the v, and it's going to be the rise up with the velocity of the u1. Here the velocity will be the u1. It's going to be taking it. So how do you calculate this particular thing? So from the E is equal to V2 minus V1 by U1 minus U2. Since both V2 and U2 are 0, they are concerned to the earth. This can be written as an V1 by U1 or minus V1 by U1. U1 is going to be the initial velocity where it is striking this one. This will be the U1 and this will be your V1. So U1 will be equal to the or negative sign indicates it's an opposite in the sense. So you can conclude this one. V1 can be written as an 2G, or it's going to rise up to the only H1, and it is coming from a height called as an H. 2G, 2G, if I remove E is equal to the, it can also be written as an H1 by H. Or from this one, H1 is equal to E square terms of the H. Like this, if you have a second collision, that is, if here it is an H2 case, then H2 can be written as an E square whole square into H1, or sorry, initial velocity, that is the H conditions, or generalized formula, if I write Hn is equal to e to the power of 2n into H1. So 2n into H, where initial velocity H can be directly written as an 2gh. So this is the velocity of the, so height of the nth rebound. So this is the height after nth rebound. N times rebounds, this is your height. Sir. So then we need to find out the velocity. So what is this velocity? So velocity of the objects, whatever you that's going to be the after nth rebound. So how can you say this one? This is Hn is equal to e to the power of 2n into h. H is nothing but an e to the power of 2n into root over h value can be written as an u square by 2g, or anything you can put it over there. Or if you want to convert that into your velocity terms, you can also write the velocity in this case also. Or if I want to find the velocity after the rebound, go for the coefficient of restitution. E is equal to minus V1 by U1. V1 and U1 both can be written as an root over, it is 2gh1 by root over 2gh2. So if I remove the 2g, then it will be the root over h1 by h2. This is your situation. Or else from this one, you can also say that V1 is equal to E times of the U1, or you can say V2 is equal to E times of the V1. But V1 can again written as an E into U or U1, whatever is going to be the. So that means Vn is equal to E to the power of n into U. So this is the relationship between the velocity and the nth rebound with an initial thing. And correspondingly, you can also find out the displacement conditions. Displacement is equal to h. That is your displacement. Whereas the distance can be written as an, that is s in the distance can be written as an h plus 2h plus 3h. So like this, it will be the total displacement. It will be in the form of, if I take the h common, it will be the 1 minus. You will be having the geometrical progression conditions. This is h1, h2 like this. Geometrical conditions you can apply. That is 1 minus e square by 1 plus e square sort of a thing, and the time period will also be coming in the same sort of a fashion for the balls which are being rebounded. So as I have told you, what is the distance traveled is, distance traveled is equal to s plus first height is going to be the h, and it is traveling h1 for the two times, it is traveling h2 for the other two times. So like this, 2 into h3 so on up to hn. So from this one, h is e plus 2 into h1 can be written as an, that is e to the power of 2n into h1 plus 2 into e to the power of 2n into h2, like that. So it's going to be the 2n means it will be the 4, it will be the 2 plus 2 into e to the power of third one. It's going to be the, that is 6h2 like that. It will be the 6 times of n value will be 3 in terms of this is h3 like that. It will be there. And when you take an example of solving this one, when you go for the solving of this one, this will be the h I am taking 2 e square h I am going to take. H1 is equal to, what is the relation between hn is equal to e to the power of 2n into initial height. So h1 will be equal to the 2 e square h. This will be the 1 plus e square plus e to the cube plus so on. It's a geometrical progression sort of a thing. That will be the h plus 2 e square of h into 1 by 1 minus e, or e square. This will be the e to the power of 4 if I have taken the e square outside like this. So this will be equal to the, that is h will be taken as common into 1 minus e square plus 2 e square h by 1 minus e square. So h will be taken common, it will be the plus 2 e square, or it can be written as an h of 1 plus e square by 1 minus e square. So this will be your derivation. This will be how much, sir? 1 plus e square by 1 minus e square. This is how you can solve for the distance. And your displacement is S is equal to H. And the time Muchetapatiki, that is the time where you can find it out. That will be, it is traveling H plus like this. It can be written as a T1, that is root over 2H by G plus 2 into root over 2 into H1 can be written as a root over, in the sense e square h by g plus 2 into root over 2 into e square h by, so like this. You can also find the time of the nth rebound like this. Okay, fine. So thank you for this session, please. Thank you for listening. Hope you have got some sort of an information regarding the corresponding chapters.